When I solve equations, however, having multiple logarithmic statements becomes a problem that I don't really want, okay? Because a mistake that students will make for part A, for instance, they'll say that the right-hand side is 20 to the first power, and they say that'll cancel both log base 20s on the left. It doesn't work that way. And I'll have some students will just totally ignore the fact there's a log base 20 there. The issue is, I mean, like for all these, the rules we use, like when we have a logarithmic equation, we turn it into an exponential equation. It only worked if we had a single logarithmic statement. Here we don't have that. We have multiple logarithmic statements. They are of the same base, which is at least good. So what we need to do is find a way of getting a single logarithmic statement. So in part A, what I'm going to do is I'm going to, use the product rule that says, well, if I have the logarithm of the same base of two different things being added together, then I can turn that into a logarithm of a product. So now I went from having two logarithmic statements down to having just one. Of course, I'm going to FOIL what I have there, but what I'm going to do is I'm going to get rid of the logarithm by now, turning this into an exponential statement. So 20 to the first power is going to equal that product. That product, of course, is going to be FOILed out, and that's what I would get. So it went from a logarithmic equation to an exponential equation, or to a quadratic equation to be more exact. Situations like these are where you start getting potentials for extraneous solutions. So you have to be on the lookout for those. Because I'm going to start solving the quadratic equation here, which means I'm going to get the set equal to 0. And I'm going to use the quadratic formula to get these two answers. Either x is going to, and I eventually whittle it all down. You see all the work there that was done. And I get that x is about 1 plus 2 times the square root of 14, or that x equals 1 minus 2 times the square root of 14. From a decimal standpoint, something that's good to see what the decimals look like. 1 plus 2 times the square root of 14 is about 8.483. Equaling 1 minus 2 times the square root of 14 is about negative 6.483. When I look at the original problems, 8.483, I could take the log base 20, of the original, two quantities if x equals that, because those would make them both positive. If I let x equal negative 6.483, if I do x minus 7, that's negative. If I do x plus 5, that's negative. I can't take logarithms of any base of negatives. So our second answer here, the one that comes out to be about negative 6.483, is an extraneous solution. So even though we came up with two solutions initially, one of them is extraneous because it just doesn't work. And therefore, that's 1 plus 2 times the square root of 14 is our one and only answer. Logarithmic equations tend to more often than not have extraneous solutions, especially the more complicated they become, or when you have to use properties to do them. So be sure you check for them. It's the moment that you don't check for it that you end up finding out that that's when it needed to be done. And you end up having an extra answer that it shouldn't be there, and you end up losing some points off of the problem because you didn't check for your extraneous solution and eliminate it. For part B, now the important thing about this one is that I have log base 7 of 16x over the log base 7 of 2x. Now, we do not have a rule for, I have two different logarithmic statements here, so that's an issue. But I don't have a rule for me dividing two different logs together. I have a rule where a single logarithm of two things being divided is occurring, but not two separate logarithms being divided. So make sure you know what those rules state, and more importantly, what those rules do not state. The quotient property does not apply to this problem. A lot of students will say it does, and they'll end up saying something like, well, that's the log base 7 of 16x minus 2x. Well, that's not what the rule says. I'm not going to take a quotient of two different logarithms and make that a single logarithm of a difference. It's when I have the two logarithms being subtracted that I can turn into a single logarithm of a quotient. So don't reverse that. Here what I would have to do is multiply both sides by log base 7 of 2x. Essentially it's like doing a cross multiplication. So I have the log base 7 of 16x equals 2 times the log base 7 of 2x. I could use the exponent property for logarithms and on the right hand side and make that the log base 7 of 2x squared, leaving the left hand side alone. Now here's what's nice about situations like these. On both sides of the equation, I have a single logarithmic statement. They are of the same base. Therefore, here is an instance where I could just drop the logarithms out. I really don't have to apply an exponential. They would just basically, well, I do square 2x first. But the log base 7s do cancel out. That kind of cancellation also brings about the potential for extraneous solutions, so I still have to be on the lookout for those. Now when I solve this equation, I have a very simple quadratic equation here. So I'm going to set it equal to 0. And I get two answers, x equals 0 or x equals 4. Now again, when I look back to the original problem, the log base 7 of 16 times 0. Okay, well, that's the log base 7 of 0, which basically says, okay, I'm looking for a power of 7 that gives me 0. Well, there isn't one. I can't take logarithms of 0. So that one's extraneous. The only solution we have is that we have x equaling 4. So again, the more complicated the logarithmic equation becomes, the more potential you have for extraneous solutions, and likewise, the more necessary it becomes for you to check to see if there are any.